Okay, here is another RC circuit problem. This is question 4 from the midterm 2 practice packet put together by Bob Johnson. So in this problem, we have this circuit. This is a little bit of a tricky switch. There are 3 places this switch can be. It can be connected to nothing, or it can connect B to A, or it can connect B to C. So initially the capacitor is uncharged. I guess it means both capacitors are uncharged, and the switch is open, meaning it's not connecting B to anything. And then we've got those component values. I wrote these things in terms of kilo ohms. So 10 to the 5th ohms is 100 kilo ohms. Then the switch is closed such that points A and B are connected. How long after this happens is the voltage on the capacitor equal to 3/4 of the voltage on the battery? All right. Whoa. So let's figure that out. So we're going to take this switch and we're going to close it such that A and B are connected like that. Okay. And then what's going to happen? I guess we're going to get a current like this. So I'll call that I. And we want to know how long does it take. So let's say at t equals 0, we connect A to B. Okay. And before, for t less than 0, Q1, whatever, equals Q2 equals 0. The capacitors have 0 charge. I think capacitor 2 is irrelevant for this part of the question anyway. And then we want to know at what time, at t equals what time, we have the voltage across the capacitor. So I guess that means Q1 over C1. That's the voltage across the capacitor equals 3/4 of the battery EMF. Okay. Let's make sure we read that correctly. Switch is closed, A and B are connected. How long after the switch is closed is the voltage on the capacitor? That's the voltage on the capacitor, meaning the capacitor being C1. Okay. Equal to 3/4 of the voltage on the battery. Okay. Gee, how long is that? Okay. Now, what do we know, like the instant after the switch is closed? I call that like t equals 0 plus. Then the charge on this capacitor is still 0. Let's write that down. So we know that at t equals 0 plus, Q1 equals 0. So that allows us to find the current. So then we can use the loop rule. So the loop rule would say the battery voltage minus IR2 minus the voltage across this capacitor, but that's 0, Q1 over C1, minus IR1 equals 0. Okay, and this quantity is 0. So this is like the instant after we close the switch, because we're going to have, I drew this before, so if we have the current versus time, then that looks like some maximum value and then it exponentially decreases. So I like to figure out like what is this value I0, and then I want to know what's the time constant, because this is like I0 e to the minus t over time constant. Though, of course, We could just directly use the charging up capacitor curve, like 1 minus e to the minus t over tau. But that would require us to know the final voltage on the capacitor. I guess we actually could do it that way. Let's do it both ways. Let's do it this way first. Okay, so this is going to give me I equals the battery voltage. This is, actually I'm going to call this I0 because this is really like, this is, yeah, once we cross this off, you see this was true always, as long as that switch is closed. But then we cross this off because it's when the charge in the capacitor is 0. And that's only true like immediately after t equals 0 plus, immediately after we close the switch. So I'll label this with 0. So I at time 0 is the battery voltage divided by R1 plus R2. Fine. We could write numbers if we wanted to. 300 volts divided by 300 kilo ohms is 1 milliamp actually. 300 volts divided by 300 kilo ohms is, it's actually 1 milliamp. All right. And gee, I don't have that written down. Oh well. Okay. So then what's the time constant? So see, what's charging up the capacitor? We have this current, and there's only one capacitor in the circuit. So the capacitance is C1, and then we have these two resistors in series. So I think our time constant is R1 plus R2 times C1, which is 300 kilo ohms times 6 microfarads. So that is 8. Gee. Okay, we have to get the exponent right. This is 1800 milliseconds. Kilo ohms times microfarads is milliseconds. 1800 milliseconds, so that's 1.8 seconds is our time constant. That's what I got before also. Okay, so then we could say that I of t is I0, which we got up here. Here's I0 times e to the minus t over that time constant. And then we can say the voltage across the capacitor. This is probably not the easy way to do this. So, well, anyway, let's do it this way anyway. Okay, so then the voltage across the capacitor is just this quantity. So we can use the same loop rule without anything crossed off. So here's like the battery voltage minus, this is the current versus time. And then here's R1 plus R2. And then I can move this to the other side. So this equals Q1 over C1, which is the voltage on the capacitor. And somehow we want this to equal 3/4 of the battery voltage, and we want to solve for the time. So this is fine. So actually we can see if we move this over here, that gives us minus 1/4, and then we can cancel the minus sign. So this is actually I times R1 plus R2 equals 1/4 of the battery voltage. Did that work? Let's see. 3/4 minus 1 is minus 1/4. And then we do the minus sign. So that's plus 1/4, and this is plus. So this is I0 R1 plus R2 e to the minus t over tau equals EMF over 4. So e to the minus t over tau equals the battery voltage divided by 4 I0 R1 plus R2. So then, okay, if I take the reciprocal of this, then it's actually e to the plus t over tau. Then that's the reciprocal of this. And then I take the logarithm of both sides. So I'm going to say the logarithm, no, I don't need the logarithm of the exponential is just the argument of the exponential. So I have t over time constant equals 4I0 R1 plus R2, which I hope is going to be less than epsilon, divided by the EMF. Okay, so this, what is this quantity? Okay, let's, oh, you know, what's kind of interesting, so this I0, this is actually, yeah, the EMF. Okay. So this is for EMF over R1 plus R2, but then there's R1 plus R2. That'll cancel. And then here is the battery EMF. So actually it's just going to be 4. Yeah, there we go. This equals 4. Okay, so T is 4 time constant. So that's going to be 4 times 1.8 seconds. So I guess that's going to be 8 seconds minus 10%. 7.2 seconds. Oh. Oh! Ha 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 ha! I forgot the natural logarithm. It's not 4, it's log of 4. Okay. Ha 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 ha. So this is, am I going to put this on YouTube for the world? This is kind of funny. Okay. This is the natural logarithm of this. Ha 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 ha. Okay. And then this is the natural logarithm of this. Okay. And this is the natural logarithm of this. Okay, so then there's the natural logarithm of 4. Okay. Sorry. Natural logarithm of 4. Okay. So there we go. So T is the time constant times the natural logarithm of 4. Okay, I don't know the natural logarithm of 4. So here this is 1.8 times log of 4. I asked Python that. It says 2.495 seconds. So 2.50 seconds. 2.50 seconds. All right. Cool. And that is the same answer I got yesterday. Let's do it like maybe the more conventional way. Okay, how did we do it just a moment ago? I said, okay, I'll have the expression here for the current through the capacitor. And I know what its initial value is because we start out with the capacitor discharged, so then that capacitor looks like a wire at the beginning, so we just have, this is 0 volts across the capacitors. This is battery EMF divided by R1 plus R2. That's the initial current. And then there's some exponential decay time, tau, And that exponential decay time is this capacitance multiplied by the series combination of these two resistors. Okay. And then now I know what the current as a function of time is, because I know the initial current and I know the time constant. And we start the clock when we flip the switch. So then I used the loop rule and I said, oh, battery voltage minus this voltage drop minus this voltage drop, the only thing that's left is the voltage across the capacitor. And then we solved that. Fine. But we could solve it a different way. We could say, what is the voltage across the capacitor after you wait a very long time? So after you wait a very long time, you see there's only one branch to this circuit. So after you wait a very long time, so here's what the charge on this capacitor versus time looks like. So here's like Q versus time, and it looks like this. So it starts out at 0, and then see here's the maximum slope, and then it like evens out like this. So this is like Q max. It's like the asymptotic value. This is when it's charging. When it's discharging, it's like the other way. When it's discharging, it has the same shape as this. So this is like the capacitance times like the maximum voltage. This is like what's the voltage on the like this Vmax is like what's the voltage on the capacitor after a very long time, or Qmax is like what's the charge on the capacitor after a very long time. So after a very long time, you see the slope of this curve is 0. The slope of this curve is the current charging the capacitor. So that current becomes 0. So if that current becomes 0, then this IR drop is 0, and this IR drop is 0. So by the time this is fully charged, which is by the time the current has become 0, the capacitor voltage equals the battery voltage. See, because you could say battery EMF minus IR2, which is 0, minus Q over C, minus IR1, and that's 0. See, here's battery EMF. This term is 0 once the current has stopped flowing. This term is definitely not 0. This term is 0. So that leaves us with the battery EMF equals the voltage across the capacitor after a very long time. So actually, see, if we drew the voltage versus time, it has the exact same shape, the capacitor voltage. And the asymptotic value of the capacitor voltage is just equal to the battery voltage in this problem. It's not always the case, but it's true in this problem, because there's no IR drop between the battery and the capacitor, like once the current through the capacitor is 0. In other words, once the charge on the capacitor is stabilized. So actually, this is actually a more direct way to solve this problem. We can say V capacitor, that's the same thing as like Q1 over C1, that equals V capacitor. This is actually, in this case, it's the battery voltage times 1 minus e to the minus t over the same time constant that we calculated over there. Oh, by the way, right, so this shape here, see, this is like, this shape, I'll write this in blue. This shape is Qmax times 1 minus e to the minus t over time constant. That's for charging up. So that's actually more direct. So then we want to know, what time does this thing equal 3/4 of the battery voltage? Is this just part A of this problem? That's amazing. Okay. So the EMF cancels, so you get 1 minus e to the minus t over time constant equals 3/4. We just canceled the battery EMF. So then we can get rid of the 1 minus. You see, this goes on to the other side of the equation. It becomes a plus. This comes over to this side of the equation, then you get 1/4. So we get 1/4 equals e to the minus t over tau. We can take the reciprocal of both sides. You get 4 equals e to the plus t over tau. Now I take the logarithm of both sides, and I remember to actually take the logarithm of both sides, and we get the logarithm of 4 equals t over tau. So that gives us that the time when this happens is 4, it's the time constant times the log of 4. Same thing. So the time when this happens is the time constant, so the time when this happens is the time constant times the natural logarithm of 4, which is the same answer, 2.5 seconds. So we answered problem A 2 different ways. And in this case, I think the second way was much more direct. Okay, so that's kind of interesting. So what do we have to do that? I mean, actually, this is kind of what you would have gotten, I think, if you just blindly plugged into the equations and you didn't think too hard. So usually the first thing to think is that the capacitor will charge all the way up to the battery voltage. That's not necessarily true. You have to look at the circuit and say, what's happening after a long time? What's happening after the current flowing through the capacitor reaches 0? So in this case, there's only one branch in the circuit. So then it really is true that by the time I is 0 flowing through this capacitor, then the battery voltage equals the capacitor voltage. And then you say, okay, now I know what the maximum value is of this curve. And then the shape is just right off the equation sheet, 1 minus e to the minus t over tau. The equation sheet lists the form for Q, the charge, but it's the same form for V, the voltage, because they're proportional with the constant proportionality of the capacitance. Okay, so then you want to know when is it 3/4 of the battery EMF, so that's actually the easy way to do it. The second way we did that was the easy way to do it. What are we going to do for part 2 of this, part B? Part B of this problem, what is the current through R1 at that time? Well, that's easy. It's 0. Okay, so here. What is the current through R1 at that time? That's easy. It's 0. Is it, specify if it's up or down. It is not up or down. It is 0. Wait, no. Oh, gosh. Oh, scratch that. Oh, no. After a very long time, it's 0. What is the current through R1 at the time? Sorry. It's not 0. This is the current through R1 at that time. In real life, I would edit these things. I would edit out the bloopers. So the current is the current through R1 at that time. It's going like this here. Yeah. So, and then it has this value. See, this is the current at that time. So I guess we kind of did need this calculation. We did. And I guess we actually needed this calculation. So here is this constant. So, okay, at t equals like tau log of 4, we have I of t, which is the current through R1, and it's up. Okay, I of t is this answer here. This is 1 milliamp, and then it's times e to the minus 4. No, e to the minus e to the minus tau log 4 divided by tau. So it's e to the minus log 4. Which is just 1/4, right? Yeah, so this is 1/4 of a milliamp. Have I confused you yet? Let me do a little more erasing, and then let's write that thing out a little more neatly. Yeah, so it is 1/4 of a milliamp, and it's flowing upward through R1, but I feel like I might have confused you. So let's let's work that out again. Okay, so the question we want to answer is when the voltage across the capacitor is 3/4 of the battery voltage, what is the current flowing and which direction is it flowing? Now there's actually, so the way I did this just a moment ago is I said, oh, let's take this expression for the current and let's plug in the time that we solved for, and then that's 1 milliamp times e to the minus logarithm of 4. And e to the minus logarithm of 4 is just 1/4. You could work that out, or your calculator can tell you that. So this ends up being 1/4 of a milliamp. But there's an easier way to do that. We could use the loop rule here. So if we use the loop rule, starting at the battery, we can say battery EMF minus I R2 minus Q1 over C1 minus I R1 equals 0. There's the loop rule. So now we just said that this is 3/4 of the battery EMF. So we have battery EMF minus I R2 minus 3/4 of the battery EMF minus I R1 equals 0. So this is battery EMF over 4 equals the desired current times R1 plus R2. So that gives us that the desired current we're trying to solve for is the battery EMF divided by 4 times R1 plus R2. So I think, well, we kind of already have the work done for that, but if we just work it out directly, this is 300 volts divided by 4 times 300 kilo ohms. Okay, and this ratio is a milliamp. It's 1/4 of a milliamp. There you go. So this is like 1/4 of a milliamp, which is like, you could say it's 250. If you wanted to, you could say it's 250 microamps. Okay, so that was a completely different way to solve that, actually. See, we said, well, okay, I know what the voltage across this capacitor has to be and everything. And I just want to solve for this current. So this voltage is given in this part of the problem, and then I just want to solve for the current. So that was kind of like a trick you could use to do it that other way. Or you could just directly plug into this expression for the exponential form of the current versus time. Wow. See, wouldn't these exams be more fun if you had like an infinite amount of time to work on them and you could try all these different ways and compare the results? What is the next part of this problem? Oh, by the way, and that current is up. Yeah, it makes sense. It's up because we're still charging the capacitor. So that current is up. Okay, now after a very long time, the switch is open so that A and B are not connected anymore. And after a very long time, the switch is open so that A and B are not connected anymore. Okay, you have to figure out what's happening there. And then the switch is closed to the right so that points B and C are connected. What is the current through R2 immediately after the switch is closed? In which direction? So to work, we're going to have to do some erasing, but to work this out, you see, with these problems where you throw the switch from one position to the other, you kind of, in order to know what's happening immediately after you move the switch, you have to know what is the state of the capacitor immediately before you throw the switch. So we have to work out the state of the capacitor, the charge on the capacitor, C1. So we have to work out Q1, which is the charge on C1, after this is like this for a very long time. What does a very long time mean? It means that we waited so long, so many seconds, like it's like 1.8 seconds is a time constant. So maybe we waited like a minute or more. Okay, maybe we waited 2 minutes. And then this current now is negligible, so these IR drops are negligible. So after that very long time, in this circuit, the voltage across the capacitor equals the battery voltage. So that's going to be our starting point for this next point when we throw the switch. So we know that our starting point for this next point, we're going to erase this, and what we're going to do in a moment is we're going to erase this, and then we're going to redraw it over here because the switch is now connecting B and C. But the starting point is like this charge on this capacitor, and here's minus Q1. This charge on this capacitor is such that the voltage across this capacitor equals the battery voltage. Okay, so let's do that. Okay, so immediately before we moved the switch, so what we did have before was that A and B were connected together, and now we left it in that position for long enough that the charge on this capacitor reached its asymptotic value. That means that the voltage on this capacitor at that asymptotic point is equal to the battery voltage because there was no IR drop across either one of these resistors once the current through the capacitor became zero. So that means that Q1 over C1 equaled the battery voltage just before we moved the switch. Then we moved the switch. So there's a resistor here. It takes some time for the charge to move from place to place. So immediately after we move the switch, this charge on capacitor 1 still equals the capacitor 1 times the battery EMF. So we want to know what is the current through R2 immediately after we move this switch. We could actually extend this problem to say what happens after that. Actually, I think it makes a much more interesting problem to say, like, what happens after that. So here you have plus charge here and minus charge here, and then this thing is 0. So the charge here is 0 initially. Here you have plus charge, minus charge. Here you have 0. So remember I said to you a couple of videos ago, gee, can we think of an example where you have two capacitors in series whose charge is not the same? Well, you see, these two capacitors are in series. Their charge is not the same yet because we started the clock with 0 charge on this capacitor and with Q1 plus Q1 here minus Q1 here on this capacitor. And then where are they going to end up? Actually, the place where they're going to end up is actually not they have the same charge. I think the place they're going to end up is they have the same voltage. So that's actually, remember I was saying, gee, I wonder if we can think of a counterexample if you watched a couple videos ago. So I think we found this is kind of an interesting example. Yeah, actually this is kind of an interesting example if you continue it all the way through, because I think what we're going to find, this is going to be confusing. Maybe this is why I didn't wind up on the real exam problem in this particular set of practice problems. These practice problems come from old exams that aren't in the exam archive. I think we're going to find that the time constant corresponds to these two capacitors being in series, but that the final state after everything is settled is going to correspond to as if these two capacitors are in parallel. Okay, anyway, let's solve the problem that's asked first. What's the current through R2? So I think it's going to be this direction. So I'll just draw current this way. It has to be this direction because we've got positive charge. So this charge, this current is going to flow. Here's a positive. See, if you say, let's just call this 0 volts, and this is some positive voltage, and then there's 0 charge here, so this is still 0 volts. So you're going to have current flow this way because this end of the resistor is at a higher potential than this end of the resistor. Or maybe you want to look at it more simply, like here's like an excess of positive charge here, so it's going to move like this way onto this uncharged capacitor plate. Do you want me to think harder about what's the sign of this? I mean, I looked at this, I said, oh, it's obvious, it's going to go that way. But then how do you really prove that? I think, you see, you could prove that if you want to, because you know that this is like a positive voltage and this is like zero voltage. So you see, we could use the loop rule here. Let's start at this capacitor. So we can say Q1 over C1, and then let's pretend the current is this way, see if it comes out positive. So then this is minus IR2, the way we drew it. Now we go back down through this, but this is, this actually, see, if you call this Q2 and you call this minus Q2, then this actually would be minus Q2 over C2, but it doesn't matter, it's zero. So like, if you get this wrong, it doesn't matter in this case because this is zero anyhow at this point. So then, so this does turn out to be positive, you see, because we get, and by the way, this initial value of Q1 over C1 is just equal to the battery EMF. So like if you say at time 0, then this is the battery EMF. That's just because that's what was stored on this capacitor from the previous part of the problem. Minus I0 R2 equals 0. So this indeed gives us a positive value for this current. That tells us we drew the arrow the correct direction. So this current at immediately after we threw the switch is just the battery EMF divided by R2. You say, what is the battery EMF doing here? The battery isn't connected. It's because that's the state that we left the capacitor in. Like, this is really, I mean, if you wanted to be more precise, you could say, like, this is the initial value of the charge on this capacitor, you know, but the initial value divided by the capacitance. So that's the initial voltage on this capacitor. But the initial voltage on that capacitor just equals the battery EMF from the previous part of the problem. So I think this current, when we first close the switch, must equal 300 volts divided by 100 kilo ohms. So that is 3 milliamps. That's what I got when I worked it out yesterday, and it's flowing upward through R2. Now, I think there's an interesting question we could ask. This is the end of this problem. So if you're tired of watching this video, and I don't blame you if you are, then you can stop. But then you could say, well, what happens after that? And I think what happens after that is that we kind of worked out a similar problem a moment ago. So I think C1 discharges, C2 charges, and you have like I is, see, it's like, here's the voltage on that first capacitor, Q1 over C1. And then here's the voltage on that second capacitor. It's like Q2 over C2. And then it's going through that resistor, R2. This is kind of like the digression we added to like 1 or 2 videos ago. So you can see like Q1 is going to decrease, Q2 is going to increase, and then this current stops flowing when these two voltages are the same. So we end when Q1 over C1 equals Q2 over C2. But meanwhile, we know that all along, see, the charge like has to be constant. The total charge is not disappearing. So we know that Q1 plus Q2 equals like that initial charge on capacitor 1. So I could call that like Q1 at time 0, but that's basically the same thing as the battery voltage times C1. So that's like, this is just a charge that we started out with on capacitor 1 when we first, before we closed the switch. So I actually kind of wrote out a solution to a problem just like this, like a video or so ago. That was where I said, oh, it would be fun if we replaced the switch with a resistor. So now this problem actually has that, except it doesn't ask you to work out the consequences. But But I think the time constant here is going to be this resistance times the series combination of these two capacitors. So that means 1 over C1 plus 1 over C2, the reciprocal of. And I didn't prove it here, but I proved it, I think, like at this kind of addendum at the end of 2 videos ago. Yeah, so I think actually, like, if you did like something here, here's like versus time, and you say like, here's the voltage on capacitor 1. It starts out at the battery voltage. So this is like voltage on capacitor 1. It starts out at the battery EMF, and then it decreases. Oh, which capacitor is well, okay, we can work out where the endpoint is in voltage, but let's not worry about it. Okay, so then it decreases like that. And then the voltage on battery, the voltage on capacitor 2 does something like this. It starts out at 0, and then it like asymptotes to like this value. And what is this value? This value is like the voltage that you would get from it's the voltage such that Q1 over C1 equals Q2 over C2. It's the same voltage on each capacitor, and maintaining the constraint that the sum of the two charges is the same as you started with. So I won't bore you by working that out. I think that's too complicated for an exam question, but it's kind of cool that we can, I think we can see how that ends. All right, this has already gone on too long, sorry.